We introduced our new unit, our fourth and penultimate unit on Tuesday, called electromagnetic radiation. We learned on Tuesday that electromagnetic radiation is caused by accelerating charges, not charged particles at rest. Charged particles at rest will produce a gravitational field. Charged particles at rest will produce an electric field, albeit a constant electric field. Charged particles at rest won't produce a magnetic field. And of course, if you're going to have electromagnetic radiation, you need both an electric and a magnetic field. So charged particles at rest won't produce EMR. Now, charged particle that's moving at a constant speed will also produce a gravitational field. It will also produce an electric field, albeit a constant electric field. And a charged particle that's moving at a constant speed will also produce a magnetic field. Although not a changing magnetic field, just a constant magnetic field. That's electromagnetic radiation, right? Because we've got an electric field and a magnetic field, but it isn't electromagnetic radiation because in order to have EMR, we have to have not a constant electric and magnetic field, but a changing electric and magnetic field. And you'll see why in just a moment. So what do we got to have? Not just a charged particle that's not moving, not just a charged particle that's moving at a constant speed, but rather we need a charged particle that's moving with a changing speed. In other words, an accelerating charged particle. That will produce a gravitational field because it's got mass. It'll produce an electric field because it's got charge. But this time, because the speed is changing, the electric field will also be changing. The magnetic field that it produces will also be changing. This is enough to give us electromagnetic radiation, the changing electric and magnetic fields. Now, why do we need that changing electric and magnetic field? Why can't it just be an electric field and a magnetic field? Let's take a look at the picture here. The diagram that you see up on the board. Let's scratch out this portion of it. We've got, let's say, a red electric field on the y-axis. We've got a green magnetic field on the z-axis. Those two are in phase with each other, meaning when we have a crest, we have a crest. When we have a trough, we have a trough. In phase with each other. Okay, two crests, an electric field wave and a magnetic field wave crest. Changing, right? Changing. Okay, it's zero intensity right here. The intensity is increasing, and then the intensity is decreasing. Same deal with the green magnetic field wave. The intensity is zero, then it's increasing, and then it's decreasing, and the intensity is zero again. So two changing waves, an electric field and a magnetic field, that are perpendicular to each other. As you can see, they're on two different axes. Now, here's the really important part. Here's why we need the changing nature of it. Okay? An electric field, magnetic field, that's great. In order for a magnetic field to cause an electric field, in order for an electric field to cause a magnetic field, we have to have a changing electric and magnetic field. So what happens is this. Okay, this red electric field will generate this blue magnetic field. So red causes blue. This electric field causes this magnetic field. That doesn't happen if that electric field wasn't changing. If it was constant, hey, it's great. You still got the electric field there, but it's not going to make the new magnetic field. Similarly, this green magnetic field that we have, if it isn't changing, then it's not going to make, what color should we pick here? It's not going to make, let's go yellow. It's not going to make this changing electric field. So that's the deal. In order to get the red electric field to make the blue magnetic field, the electric field had to be changing. In order to get the green magnetic field to make the yellow electric field, then the magnetic field had to be changing. If they're constant values, you still have this, but you don't have this anymore, the new electric and magnetic field. And that's critical to the whole notion of electromagnetic radiation, because if you don't have more electric and magnetic fields made, and then in turn, more electric and magnetic fields made, and then in turn, even more electric and magnetic fields made, then you don't have electromagnetic radiation. You just got a simple electric and a magnetic field. Now, as this blue magnetic field and this yellow electric field are produced by the green and red magnetic and electric fields, what happens to the originals? They disappear. They're gone. You can't create energy from nothing. If you had energy right here, and it made this, well, then the energy from here has to be transferred to this. So now this little wave pulse that you had at the beginning over here that was caused by some accelerating charge, that energy is now moving, it's transmitting, it's propagating along the x-axis from one place to another. So this causes this, and then this disappears. This causes this, and then this disappears. This causes this, and then this disappears, and so on, and so on, and so on. Now, it disappears if the source disappears. If the source continues to accelerate, we get oscillating motion. This charge accelerates, speeds up, slows down, stops, reverses direction, speeds up, slows down, stops. And if it keeps doing that, if it keeps going back and forth like this, then when this little spot disappears, well, it gets replaced by another one. And then when it disappears again, it gets replaced by another one. So what you end up with is not just this, this wave pulse like we represented in this diagram, but rather we get the full continuous electromagnetic wave. Make sense? So what is this exactly? We know it's caused by accelerating charges. We know it consists of changing electric and magnetic fields. What is it? It's energy. That's what waves are in general, energy. We talked in Physics 20 about mechanical waves, waves that travel through the water. Okay, that's energy. You jump into a swimming pool, somebody else is over there sunning themselves on the air mattress on the other side of the pool trying to read a book, and all of a sudden they're bobbing up and down. They're bobbing up and down because your kinetic energy as you jumped into the pool is transferred to them by the waves. Waves carry energy. These waves do too. They just do it without the need for particles, without the need for the water to carry the energy. Okay, this is pure energy, and it can travel through empty space because it's carried by electric and magnetic fields as opposed to the water particles or the slinky particles or the air particles or whatever. Right? How fast does it travel? Boy, how fast does it travel? It travels really fast. Okay, 3 times 10 to the 8 meters per second, which if you multiply that by 3.6 kilometers per hour, it's about 1 billion kilometers per hour. It's just give or take. Okay, at that point, you're talking about 1 billion kilometers per hour. It doesn't really matter exactly how fast it's moving. It's really, really, really fast. Right? Nothing can travel faster than the speed of light. Good? Ringing a bell, guys? Just stuff ringing a bell from Tuesday. It's been 2 days now. You wrote a test in between, but it's all good. We talked about the wave nature. We alluded to the particle nature of EMR. Newton thought light was a particle. Lots of other people thought it was a particle as well. Lots of people thought light was EMR. Electromagnetic radiation was a wave. Well, when Maxwell comes along and says it's really electric field wave and magnetic field wave, pretty hard to, yeah, it's not a very good diagram, I guess. You know what I mean, though, right? Okay, you know what I mean from the diagram that we drew before. Maxwell comes along and says it's electric and magnetic field wave. We got all this disagreement. It's a particle, it's a wave, whatever, but Maxwell says, but wait a second. There's all these properties of waves that are exhibited by EMR, like refraction, for instance. Refraction, if you remember, is the bending of a wave. Wave changes direction when it goes from one medium to the other, and it does that because it changes speed. If it speeds up, it bends further. If it slows down, then it bends less, changes direction less. That's a property of waves, but EMR undergoes refraction, so EMR's got to be a wave. Diffraction, same deal. This is the spreading out of a wave. Waves spread out. When they go through an opening, they spread out. Well, that's a property of waves. And so does EMR. Visible light, we'll do a little experiment later on where visible light will spread out as it goes through an opening. It diffracts as it goes through an opening. It's a property of waves, so EMR's got to be a wave. Interference is related to diffraction. If you get two diffraction openings, then waves will go through both of them, and then they're going to interfere with each other. Well, EMR does that too, so got to be a wave. Polarization, we talked about what that was on Tuesday. Probably didn't know what that was before then. Polarization is the filtering out of all but one component of a wave. The end property of wave. EMR undergoes polarization as well. You saw it with your own two eyes. Okay, when I held up the two polarizing filters and rotated them, you saw polarizing light being polarized. So EMR undergoes polarization, got to be a wave. Now this, oh goodness, this you know like the back of your hand, right? We played the song on Tuesday and played it several times on repeat as you were walking into the classroom here today. You're going to remember that song, and you're going to remember the order of electromagnetic radiation. The only thing that you got to kind of remember in addition to the song is what we're ranking them in terms of. We can classify electromagnetic radiation, the different types, in terms of three different things: frequency, energy, and wavelength. Frequency and energy go the same way. So radio waves, microwaves have the lowest frequency. They also have the lowest energy. So as we go from radio waves all the way through gamma rays, we're increasing the frequency. We're increasing the energy of these waves. As we go from radio waves to gamma rays, however, we're decreasing the wavelength. So we're starting off with a low frequency. We're starting off with a low energy. We're starting off with a high wavelength. If we're asked to rank these in terms of increasing frequency, it's, hey, it's the song. If we're asked to increase them rank them in terms of increasing wavelength, it's the reverse of that. So what you do in that case is write them down according to what you learned in the song, and then go backwards. Gamma rays, X-rays, ultraviolet, and so on. On Tuesday, we grouped them together. We said radio waves and microwaves kind of go together. Infrared, visible light, ultraviolet kind of go together. X-rays kind of by themselves. Gamma rays kind of by themselves as well. And then we talked about what causes specifically, not just in general what causes EMR, but specifically what causes each of these types of EMR, radio waves, microwaves, and so on. We said that radio waves and microwaves were produced by, does anybody remember this? Yep. Good, oscillating electric charge, which really means what? Not spinning necessarily. Oscillating means back and forth, back and forth, back and forth. Okay, so these are all produced in one way or another by electric charges going back and forth, back and forth, back and forth. Okay, we said radio waves are produced by AC current in your houses, because that's electric current, electrons that are going back and forth 60 times per second. That's pretty low frequency radio waves, but still radio waves nonetheless. Infrared, visible light, ultraviolet, well, they're all produced by transitions of electrons. Who's in chemistry or who has taken chemistry? Okay, most of you. You guys know that there's levels on electrons, right? It's not just electrons orbiting around wherever they want. They're on the first level or the second level. I think you get, I always forget the numbers, but I think it's 2 on the first level, 8. What's the third level? Is it 8 or 18 or something like that? 8? 8? Okay, 2, 8, 8, whatever the numbers are, right? We have electrons on those levels. Well, they can jump to a higher level if they absorb energy, but they don't want to stay there. If there's a vacancy down on one of the inner levels, then they fall back down to take that vacancy. It's kind of like, hey, hockey game next Tuesday night, Flames game at Saddledome, playoff game number 3. They're going to be up 2-0 at that point. You buy your $100 Sport Check Zone tickets, and you're like, wait a second, I see 2 seats in the bottom deck that cost $400 each. They're empty. What are you going to do? You're going to go down and you're going to take those seats, right? You're going to drop down levels and you're going to take the best seats that you can take. Okay, that's what electrons do too. They drop down levels and fill in the vacancies. So as they do that, they give off EMR. Hey, what do you do, Ryan, when you go from the Sport Check Zone down to row 3? You let out this little shriek of glee, right? Look at me, look at me, look at me. I just got 2 great seats, $400 each, paid $100 each for them. Okay? You give off energy as you do that. And that's what electrons do as well as they fall to a lower level. So we're talking here about infrared, visible light, ultraviolet being produced by transitions of electrons in atoms. Electrons on higher levels falling down to lower levels to fill in vacancies. Electrons on the 3rd deck, the sport check zone, dropping down to the 1st deck, good seats, okay, to fill in the vacancies. That's when infrared, visible light, ultraviolet, occasionally actually X-rays can be produced in that way as well, but usually just these 3. The bigger the transition, okay, you're going from deck 3 to deck 1, okay, you get a higher frequency, higher energy EMR produced. If you're just going from, going from the 1st deck, row 7, to the 1st deck, row 3, you're going to be happy, but you're not going to release as much energy, and therefore it's going to be a lower frequency type of EMR that's produced. X-rays. Well, we said that X-rays can be produced by this method, but not usually. Usually X-rays are produced by a rapid deceleration of the electrons. So here's the deal. Get them going ridiculously fast, like ridiculously fast, 10 to the 6, 10 to the 7 meters per second. And then you put this target in front of them, and you let them smash into this target. And when they do that, they stop almost instantly. It's a massive deceleration. The energy's got to go somewhere. They had a lot of kinetic energy, and now they got nothing. So where does that kinetic energy go? It goes into EMR, produces a photon of X-rays. Go to the dentist's office, and they put that thing beside your mouth, and they zap you. Well, it's not that thing that's causing the X-rays. It's some part of the machine over there that's accelerating the electrons to incredibly high speeds, rapidly decelerating, and then the X-rays are just being for lack of a better term, just shone on your, or exposing your teeth through that little thing that they're putting next to it. Gamma rays, finally. Gamma rays are produced by nuclear decay. And what do we mean by that? Well, the atom splits. The atom splits, literally. And when the atom splits, you're converting matter to energy. If you're not really thinking real hard right now, that's probably fine. If you're thinking hard right now, and it's like, wait a second, matter to energy? We learned about the law of conservation of energies that says you can't create or destroy energy, and you can't create or destroy matter either. Well, we lied. You can. We'll talk more about that in our last unit. You can, but under very limited circumstances. And there is an asterisk beside it as well. You can, but. Okay? So the conversion of matter to energy, nuclear decay, is what releases gamma rays. All right, finally, last little thing here that's review for us. It's a biggie though. There are 7 different frequency ranges that we got to remember. There are 7 different wavelength ranges that we got to remember. There are 7 different energy ranges that we got to remember. A little bit of good news, we don't actually have to worry about the energy until the last unit. So for now, it's only 14 things that we got to remember. A little bit more good news, there's really only 3. Okay, if we remember 3 different frequency ranges, then we should be okay with all the other frequencies and all of the wavelengths. So here's what I want you to remember, and hopefully you remember it already, because we talked about this on Tuesday. The frequency range of microwaves. Anybody remember what it is? Parker? Good, 10 to the 9 to 10 to the 12 hertz. So anything below that, radio waves. Anything above that, until it gets to visible light, is going to be infrared. Visible light, we got to be a little bit more specific for visible light. Okay, for microwaves, it's good enough just to know the exponent, just to know the power of 10. But for visible light, it's a pretty narrow range. We can only see a really, really narrow range of electromagnetic radiation. So because it's only within 1 power of 10, we want to know the base as well. This is going to be 4 to 7.5 times 10 to the... Good. Good. 4 to 7.5 times 10 to the 14. And then finally, X-rays, the only other one we have to memorize. 10 to the, back to the base, because it's a big range. 10 to the 17, 10 to the 20. Hey, if you want to remember all the frequency ranges, the other 4 that I haven't listed for you, be my guest. But I'm not going to join you. Yeah, I'm not going to memorize those. Yeah, I can barely memorize these, let alone all 7 frequency ranges. Why would we memorize the other ones? If I get a frequency that's 10 to the 13, hey, we know what it is. We know that it's infrared. If I get a frequency that's 8.9 times 10 to the 14, hey, we know it's ultraviolet. You can be given any frequency, and you can identify what kind of EMR it is based on what its frequency is. Now, what about wavelength? Should we remember 3 different wavelengths? No. What should we do? If we're given a wavelength, you should calculate the frequency. Take the speed of light in a vacuum. It's sometimes called c, 3 times 10 to the 8 meters per second. Divide it by the wavelength. And when you do that, you get a frequency. Now let's compare the frequency against the 3 ranges that we memorized here. So, for instance, okay, let's take a wavelength, for example, that is, let's say, 6 times 10 to the negative 7 meters. We want to know what type of EMR that is. What are we going to do? Well, let's say frequency is equal to 3 times 10 to the 8. That's the speed divided by the wavelength, which is 6 times 10 to the minus 7. Do the math there. It works out to be 5.0 times 10 to the 14 hertz. What kind of EMR do we have? What kind of EMR is it? Visible light. So we didn't memorize, well, there's 4 frequencies that we didn't memorize. There's 7 wavelengths that we didn't memorize, but yet we got a wavelength, we converted it to frequency, and we still determined what kind of EMR it is. You'll do something similar to that with energy as well. I'm just not going to give you the equation yet until our last unit for energy. Trust me, though, by the end of the year, you'll be able to do the exact same thing with 21 different things, not just with 14 different things. Good? Today I want to talk about how we detected EMR, how we observed EMR experimentally. Okay, throw that word experimentally in there because in the end, since the days of Adam and Eve, we've detected EMR. As soon as one day Adam opens up his eyes and says, hey, look at that nice apple tree, we've detected EMR. Because EMR is, one type of EMR is visible light. Okay? If he sees something, then we've detected EMR. So we've been detecting EMR in one way or another from the beginning of time. But how do we experimentally detect EMR? How do we detect EMR knowing exactly what it is that we're observing? Well, a guy named Heinrich Hertz introduced an experiment they call the spark gap apparatus. You should recognize this guy's name, Hertz. Where have you seen that before? Heinrich Hertz. Sorry, not Heinrich Hertz. Heinrich Hertz. Isn't Hertz the unit for frequency? Do you think it's a coincidence that Heinrich Hertz is the first guy to do an experiment to be experimentally observe electromagnetic radiation, and he gets a unit for frequency named after him? It's not a coincidence at all. He did a lot of work with electromagnetic radiation, more than what you're going to see today. He deserves to get a unit for frequency named after him, a unit for something to do with EMR named after him. So how did he do his experiment? How did he set it up? He used what's called a transformer. Years ago, I would explain to you exactly how a transformer works. We don't have to know that anymore. You have to know Hertz used this apparatus, but you don't need to know the details of how the transformer itself works. So we'll kind of gloss over that. If you have questions on it, then by all means ask them. Otherwise, we'll focus on the really important part over here. Basically, what the transformer does is changes a low voltage or a low potential into a high potential or a high voltage. So you got a few turns of wire over here, you got a lot of turns of wire over here, you got a couple hundred volts on the left-hand side, you got several thousand volts on the right-hand side. That's it. That's what a transformer does. How does it do it? Doesn't really matter. Why do we want to do that? Well, because on the right-hand side, we call the secondary side, we got a wire with a little bit of a gap in it. So it's not a full circuit. If you got a little voltage, a little potential difference across that gap, then nothing's going to happen. But if you got a big potential difference or a big voltage across that gap, then electrons will jump across the gap. That's what we want. That's the goal, to get electrons to jump across this little gap that we call the spark gap. The reason we want them to jump across that gap, because they accelerate when they jump across the gap. The charged particles, hey, look, they're sitting here. They're just sitting here. They're saying, hey, look, there's a gap. There's a bridge that's out. There's a little river here. We want to go across that river, but there's a bridge out. We can't go across. Then all of a sudden, they get a big enough potential difference, kind of a kick in the butt, where they actually jump across that river. They jump across the gap. When they jump across from being at rest to moving, they accelerate. And according to Maxwell's theory, when they accelerate, they generate EMR. So we're trying to test that theory here, right? We don't know that when they accelerate that they will generate EMR. We think they will. That's what we're trying to test. So how does Hertz detect it? If EMR is produced there, how does it detect it? Well, it puts an antenna. That's what you do, right? You want to listen to the radio, what do? You hook up an antenna to your radio because that detects EMR. How does it detect EMR? Well, what's it consist of? Changing electric and magnetic field. The changing electric and magnetic field produces a current. So if there's EMR present, you get an electric current produced in the antenna. So antennas work. You got an antenna in your car, or outside your car, I should say. Usually you don't put the antenna inside your car. An antenna on the hood of your car. Radio waves hit it all the time. Those radio waves, because they consist of changing electric and magnetic fields, generate a current in that antenna. And that current goes to your radio. And then your radio filters out that current and changes it to a sound. You hear it. So basically what Hertz is saying is this. If Maxwell's correct in saying that accelerating charges generate EMR, and if Maxwell's correct that EMR consists of a changing electric field, changing magnetic and electric field, then when I flip on this switch right over here, get this whole thing fired up, then these charged particles that jump across this gap should cause an electric current in the antenna. So if Maxwell's theory is correct that accelerating charges generate EMR, and EMR consists of the electric and magnetic field that are both changing, then flipping on the switch over here should cause a current in the antenna. Guess what happens? When it flips on the switch, there's a current produced in the antenna. The only way we get a current produced in the antenna is if we have a changing electric and magnetic field. That's what Maxwell said EMR was. The only way we get a changing electric and magnetic field is by this accelerating charged particle. That's what Maxwell said would cause changing electric and magnetic fields. So we've just, or Hertz at least, has just experimentally observed EMR, has just experimentally verified Maxwell's, or supported, I should say, Maxwell's theory. What kind of EMR did he use? Well, at the time, he wouldn't have classified it, because at the time we didn't have classifications for EMR. It was Maxwell's theory that it even existed. He detected a certain kind of EMR here, of course, even though we didn't have a name for it, it still had a certain frequency. He called that frequency, he named that type of EMR that he detected radio waves. Listen, you're the first guy to see him, you get to name him whatever you want. He named them radio waves. Why was it radio waves that he ended up using? Because radio waves are such low frequency, they're the easiest to make. It wasn't by design. He didn't say, I think I'm going to use radio waves to detect here. He's like, I'm going to produce this EMR the easiest way that I can. The easiest way to do it is to generate radio waves because they're just produced by oscillating charge. Okay. Let's have a look at a few check and reflect questions from chapter 13, page 647. Number 1 and 2, 5, and then 7 to 14. So 1 to 14, everything except the 3, 4, and 6. Give you a chance to work on that now for a little while. We're going to take a look at just a couple multiple choice questions. The first one being multiple choice number 98. You have your new worksheet / multiple choice booklet. So if you can't see it on the board, you can take a peek in there. It's going to be near the beginning. I'd like you to submit this one, please. Submit this one, please, as multiple choice number 1 on your phones. Okay, have a look at this, please. Question number 98 says, gamma radiation can be produced by what? Well, we learned that radio waves and microwaves are produced by oscillating electric charge. We learned that infrared, visible light, and ultraviolet were produced by transitions of electrons and atoms. We learned that X-rays were produced by rapid deceleration of electrons. And we learned that gamma rays were produced by, what do we say, nuclear decay, when matter was converted to energy. Which answer here sounds the most like nuclear decay? It's going to be A, radioactive decay. Okay? We didn't mention that word, radioactive, but it's the same thing. Okay? By the end of the year, it would be clear to you that radioactive means the same thing as nuclear decay. Even now, you probably could surmise that. Let's take a look at another one here. Number 100. Let's submit this one, please, as multiple choice number 1 as well. All right, guys, we've got a little bit of disagreement over this one. This one says selected regions of the EM spectrum. We got television, AM radio, gamma radiation, ultraviolet, visible light. We want to rank these in terms of increasing wavelength. Well, the first thing that we want to do when we're ranking them in terms of increasing wavelength is think of it in terms of increasing frequency, which is the exact opposite, right? But the way that we learned the song, the way that we learned to memorize them was in terms of frequency. So let's list them all. Let's list them all in terms of increasing frequency. Okay, you guys know we have radio waves, we have microwaves, we have infrared, we have visible light, we have ultraviolet, we have X-rays, and we have gamma rays. That's increasing frequency. Increasing wavelength is going to go the other way. So let's look at these now and try to identify them as radio waves, microwaves, infrared, visible light, and so on. And then let's try to rank them from gamma rays all the way down through radio waves here. Television and AM radio. That's a little bit confusing, actually, because television and AM radio are both radio waves. Both radio waves. Well, the other ones, these are pretty clear, right? Gamma rays, ultraviolet, visible light. We know that gamma rays are going to have the lowest wavelength, so this one's going to be first. Okay, ultraviolet is going to be next. Visible light is going to be next. And then, oh, which is it? Which comes next? Television or AM radio? Well, let's see if we can deduce it from the answers that we have there. Gamma rays have got to come first, so that's going to be 3. It means it's going to be either A or C, right? B and D can't be right. What comes next? Ultraviolet, which is number 4. So it's going to have to be C then, isn't it? It's going to have to be C. So we've got gamma rays, we've got ultraviolet, we've got visible light, and then it looks like we've got television and AM radio waves. So what they're saying here is that if we classify television and AM radio waves, then AM would go here and television would go here. Did we learn the difference between television and radio waves? No, we didn't. Did we need to know the difference between television and radio waves? No, we didn't. Okay, you got to know that radio waves are going to appear after microwaves in terms of increasing wavelength. Okay, but if you had to know the difference between radio waves and AM radio waves and television, then you can deduce that from the answer set. Make sense? Answer is going to be C for that one. All right, you got one more multiple choice, and then we'll leave it at that for the day. This is number 102. We'll ask you to, you know what, just do this one. Don't bother submitting it since it's a numeric response. We'll take a look at it in about 2 minutes. Last one to look at today. We've got 4 sources of electromagnetic radiation. We got to rank these, but before we rank them, then we have to identify what it is exactly that, what type of EMR it is exactly that we have produced by these sources. We want to rank them in terms of, no, sorry, we're not ranking them, are we? We're not ranking them in terms of order. We're just looking at each of these types of EMR and then looking at what causes each of these types of EMR. All right, let's start with gamma rays since we've got that one listed first here. Gamma rays produced by movement of outer electrons to lower orbitals? No. Okay, that would be, what kind of EMR would that be? Forget about down here for a second. What kind would that be? It could be visible light. It could be visible light. It could be infrared, and it could be ultraviolet, right? What about the next one? Deceleration of high-speed electrons. Rapid deceleration of electrons. That's going to be X-rays, right? Decay of radioactive nuclei. Nuclear decay, that's going to be gamma, and that's what we wanted first, right? So this is going to be a 3. Rotation of an armature in a generator? What? What are you making with a generator? You're making electric current, right? Electric current, AC electric current, that is alternating current. Electric current is going back and forth. What's another word for alternating or going back and forth? Oscillating electric charge. What kind do we have here? It's going to be radio waves, right? All right, let's look at it. So we got gamma rays, which is number 3. Okay, good. Visible light, which would be number 1. X-rays, which would be number 2. Extremely low frequency waves. I don't like that term. Okay, but in the end, again, just like in the last question, we're okay with this. We're seeing a slightly different term here because we can deduce the answer from the question. Okay, it's the only one that's left. I don't like that term though, because in the end, it is going to be ridiculously low frequency radio waves, but it's still radio waves. It's still a radio wave. Okay? They're just kind of calling it a kind of a subcategory of a radio wave here. Just like television was, and just like AM radio was, right? Subcategories. Just like red, orange, yellow, green, blue, indigo, and violet are subcategories of visible light. We're just not nearly as familiar with subcategories of other kinds as we are with visible light. So 3, 1, 2, 4. How many people got that answer? Good. Excellent. All right. Finish up your check and reflect questions. If you haven't finished them already, that's your homework. And otherwise, that's it for today.